Okay, let's draw ourselves a molecule. We have a carbocation right there. Is this legal? In organic chemistry terms, come on, people. Is that a valid resonance structure? All right. So how many hydrogens are on this carbocation?
Two.
Only one. How many hydrogens are on this carbon? Only one. Do atoms move in resonance structures? No, they don't. So by golly, people, class, if you're moving hydrogens or any atoms, then you know you've done it wrong. 100% wrong. You only move electrons. What if I try something like this? What if I have a carbocation there? Is this a valid resonance structure? Is that valid?
No.
The people that are saying no, why not?
You lost hydrogen.
I lost a hydrogen?
Yeah.
No, I didn't lose any hydrogen because atoms don't move.
Breaks the octet rule.
So I know where you're going with it, and you are right in a sense, but think of it in regards to that no atoms have moved. So how many hydrogens are on this carbon right there? 3. So how many hydrogens are on that carbon then? Do atoms move in resonance structures? No. So if there's 3 here, how many have to be here? 3. So if you draw in those 3 hydrogens, do you see a problem? What have we just done? That's a Texas carbon. That cannot happen. That is not a resonance structure. Does that make sense?
Yes.
So you have to watch out. And so when students come to me and like, hey, they will basically come to office hours and then shove in my face, does this resonance structure work? And they'll just show me this part. Okay, they'll be like, hey, does that work? I'll be like, you tell me. And when I say that, you need to draw what you just proposed with that orange arrow. Now evaluate what you just drew. Why is this doing this? Do you see what I'm saying? If you have a question, does this resonant arrow work? Draw the other resonance structure and evaluate to see if you've broken any octet rules. You can also evaluate the formal charges. What's the overall charge on this guy? A +1. What's the overall charge on that guy? +1. If you check the formal charges and they're different, the overall charge is different, then you know you made a mistake. Okay, because the overall charge of the molecule has to remain the same. Now let's introduce some heteroatoms. What if I had something like this? Could you draw a resonance structure for that? What if I took that lone pair, brought it, and stuck it between the nitrogen and the carbon, and then took that and put the electrons there? So now we have a double bond between the nitrogen and the carbon, and we put the 2 electrons on that carbon. Is that a correct resonance structure? Not yet, it isn't. What am I missing? Charges. That nitrogen atom has 4 bonds, so that's positively charged. And then this carbon right here has 1 hydrogen, 2 lone pairs, so that has to be negatively charged. The molecule on the left is neutral. Is the molecule on the right neutral? Yes, it is. A negative and a positive cancel each other out. So the overall charge on this molecule is neutral, and the overall charge of that molecule is neutral. So when I'm trying to double check my work, that's what I'm looking for, the overall charge of the molecule. Yeah.
Can electrons like skip an atom, like, or does it always move to like the one closest to it?
It cannot skip atoms. It goes right to the adjacent one. That's a good question. So if we come back to an example that many students make this mistake right here. What if we had a molecule that looks like that? Okay? Could these pi electrons come and go clear over there? And go like that? Is that possible? No, it's not possible at all. And the reason why is, what is the hybridization state of this atom, or that carbon? sp2. That one? sp2, and this carbocation? But what's that one? That's sp3. Okay? So when we're doing resonance structures, those electrons in the p orbitals need somewhere to go. And so if I'm trying to bring these electrons clear over here, it doesn't skip. It actually goes through the bonds. And since this carbon right here is sp3 hybridized, there's no empty p orbital for the electrons to get dumped into. So this pi bond right here is just stuck in that spot. It cannot move. And so those pi electrons, in this particular example, we can call those pi electrons localized. Okay, because they're just stuck in that spot. But when we come back up here to this example, we can see that these pi electrons here can move because it's adjacent to what? A sp2 hybridized carbon. So there's an empty p orbital. So those are delocalized. Basically, those electrons can move around. Okay. Now this brings up a good example here. Let's compare and contrast this molecule here. Let's draw another there. Okay. So what type of amine do we have here? What degree? Secondary. Okay. And what degree of amine do we have for this guy up top? Secondary as well. Perfect. Okay. So we still have a lone pair here on that nitrogen. Can I take that lone pair and do that? And like I said, if you have that question, can that happen? Draw the freaking problem at the very end of it. And I said I took that lone pair and I stuck it there. So now that has 4 bonds. Is that possible? Why not? Do you see the problem? We have a Texas carbon. That cannot happen. So we just say, no way, that does not happen. But why does this lone pair, why can't it move? Because that carbon is sp2 hybridized. Right? It can move down. This guy right here is sp3 hybridized. So what we have here is this lone pair right there. We can classify those lone pairs as delocalized. And then this lone pair in this molecule is localized. Meaning that lone pair right here can't move. It's just stuck. It's stuck on the nitrogen. So this raises a good point that you're going to hate me for, but don't shoot the messenger. I'm just telling you how we understand chemistry. And you guys can cry about it or just accept that's what it is and learn from it. Okay? So let's come back to this idea of localized and delocalized electrons. If I draw a amide right there, we take a look at that amide nitrogen. What is its hybridization state? What did you say? sp3? Why do you say sp3? Because there's 4 groups around it, right? That's what you've been taught. So we're going to say that is sp3 hybridized. But that lone pair, it's not localized. It can move. So if we take that down there, and there's already those lone pairs there, now if I just left it like that, is that okay? No, because I just formed a Texas carbon. So I have to break this bond and put the electrons there. Okay, we'll draw our resonance structure. So that has to have a double bond. And now we have a negative charge and a positive charge. Right? That's a valid resonance structure. Now, using what you know, what's the hybridization state of that nitrogen atom? It's sp2 because it only has 3 groups. It's sp2. So if we come back to my analogy, if you have, let's say, a blue horse and a red donkey, and they get together to form a mule, that's going to be a purple mule. Does that purple mule identify one day as a horse and then as a donkey the other day? Can it go back and forth? No, it's just a mule. Okay? And so when we ask how or what is that nitrogen, what is its hybridization state? Does it go back and forth between sp3 and sp2? No. It's a hybrid. So, but what is it? And for our class, when you take a look at the 2 hybridization states, sp3 versus sp2, you just pick the lowest number between those 2 versions. Okay, so when I draw a amide that looks like this and say, what is the hybridization state of that? You're going to say sp2. Every single time. And if he's like, well, there's 4 electron groups around it. No. Because those electrons right there are delocalized. They can resonate. And when they resonate in, it looks like this. So if I asked you, what is the hybridization state of this oxygen? What would you say? sp3? You're wrong. Because what can happen to that electron right there? It can resonate down. That can come back over there. And when I bring that electron down, it's delocalized. What do I get? It turns it into this guy. So this oxygen right here is sp2. Because when you take, let's clean it up. Okay. Okay, we have that version. And that version. What did I tell you to do? We might call that sp3 because there's 4 groups around it. But when we look at that oxygen atom, there's only 3 groups around it, so it's sp2. So what do we do when you have the choice between the 2? You pick the lowest number. So what is the actual hybridization state of that oxygen? sp2. Because we have that guy. If that comes down, goes like that, we go from there to there. Okay? So what you have to be aware of, I'll get to you in 1 second. What you have to be aware of is identifying, are the electrons localized or delocalized? You need to be able to look at a structure and ask, is there a resonance structure? All right? Question. No, because let's put on a hydrogen. It's still the same amount of groups. Hydrogen, hydrogen.
No, like right next to the end.
Right next to the end. So if I drew it like this,
Yeah.
that's saying the same thing. That hydrogen that I just drew is actually like that. There's a bond. Yeah, there's no such thing as two atoms just hugging each other. Okay, getting right up close to one another. Why are they next to each other? Because there's a chemical bond between them. It's just when we draw our zigzag structures, sometimes we just don't draw out those bonds. Yeah.
So would the nitrogen also
So with the nitrogen,
be sp2 as well?
yeah, the amide nitrogen is sp2.
If we just had an amide without the resonance structure, without the curved arrows, and we're asked the hybridization state, would it be sp2? Would we have to know that this would have a resonance structure and that those electrons are delocalized?
What do you think, class? Did you hear his question?
Yes.
So if I draw just a random amide, what's the hybridization state of that nitrogen? sp2. Alright? I don't have to say, draw a resonance structure and tell me the hybridization state. I don't have to do that. I'll just give you a molecule, and if you want to look to see if there's a resonance structure to help you answer that question, that's what you have to do. Question right here.
When it comes to functional groups, what would you say are the certain functional groups you think of?
Okay, he's asking, he wants me to make you a list of what functional groups can resonate. I'm not doing that.
Not that. I mean, like, if we're looking at something, right, and you see a functional group in one, but not the same functional group in the other, can we say the functional group is still there? Can we say it's not there?
So you're saying that's an amide on the left, and the thing on the right is not an amide?
Well, no, I'm just saying, if the functional group is not present in both of them, do you still say, is it possible for it?
That's an amide on the left, that's an amide on the right. Same thing.
Yeah, I'm talking about the possibility if it wasn't. Is that not a possibility?
So you're asking if it's possible that if I say this is an aldehyde, all of a sudden it can spontaneously say I'm an alcohol?
So they say it's not possible.
How's that possible? Let's think about that. If you look at an aldehyde and compare that to an alcohol, what's different? Here's an aldehyde. Here's an alcohol. Is that even possible to do a resonance structure that changes the functional group? You all should be screaming, heavens no, because what has happened? A hydrogen has moved. The only way to change a functional group is for atoms to move around, not electrons. Does that make sense? Good question. Yeah.
If it's like a acyl halide instead, can it still take the electrons even though if the other one's like fluorine, it's more electronegative? Can it still take the electrons from that one?
Like this? Yeah, that is still localized. Delocalized, sorry. Yeah.
So what is like the electronegativity?
Electronegativity has to do with the fact that, is that a likely possibility? Is that likely? Does the fluorine, is it willing to give up its electrons that easy? No. But it's still a valid resonance structure. It's just not. So based off of question 7, I said rank them on which is most significant. And so that's what we're going to go through to the next step, is how can we look at resonance structures and say, hey, does that make sense? Is that possible? And then we can, because when you draw resonance structures, you could draw for one molecule, you could draw like 6 of them. All right? And of the 6 resonance structures, which one is the most significant? They're not all created equal. Right? Resonance structures, there's a hierarchy of who's best and who's the worst. All right? No equality with resonance structures. Okay? But before we do that, I want to test you guys out. I have taught you some principles. All right? I've done my job. So check, like I've done it. Now do you understand it? Goodness. What is the hybridization state of that oxygen atom in this ester? Some people said it. By show of hands, who think it's sp3? No one. Well, we have a couple. So who thinks it's sp2? And then all those people who didn't raise their hand, no extra credit for you. Can you draw a resonance structure? So what's the hybridization state of that oxygen atom? sp2, because you have a delocalized lone pair. So what's the pattern here? When you have a lone pair on a heteroatom that's adjacent to a pi bond, they can move. Okay? Now, if we move on to this idea of ranking resonance structures, if we come to the textbook here, okay, section 11 in chapter 2, there's rules 1 through 4, okay, on helping us to figure out the relative significance of resonance structures. I'm not going to write these rules out for you. You guys can go to your textbook after class and look at this. But you need to know that these rules exist. And when you analyze resonance structures, you have to look at this list and follow it in order. Look at Rule 1, Rule 2, Rule 3. And the major mistake a lot of people do is they want to take shortcuts and they'll just jump to Rule 3 and make a decision and they stop it. Listen to what I'm telling you, people. 1, 2, 3. You have to go in order. No shortcuts. So I'm going to hide this now, okay? And we're going to go through this with some examples of what this means, okay? So rule 1. Let me write the molecules first here. Okay, so we have these two resonance structures. And what we want to say is which one of those two is the most significant. And what I say most significant is that we want to get to the point where we can draw a resonance hybrid. What does this molecule actually look like? It's not the one on the left, it's not the one on the right, but it's a hybrid of all the resonance structures. And so we have to figure out which hybrid or resonance structure is more significant than the other. Because the more significant one is going to make it look more like that. And the least significant is going to not really influence what it looks like too much. And this will make a whole lot more sense once we get through this whole spiel here. Okay, so rule 1, I'll just read it to you. Don't write it down because it's in your book, okay? Just listen to my words here. The most significant resonance forms have the greatest number of filled octets. So the resonance structure with the most filled octets is going to be the most significant. So we have to analyze each atom. This carbon has an octet. This oxygen has an octet. This carbon does not. It only has 6 electrons around it, but that carbon does have an octet. Now we do the same thing over here. Octet, octet, octet. Do you see? So which structure is the most significant? This one, because all the atoms in the structure have an octet. Minus the hydrogens because they can't have an octet, right? They can only have 2. So that's rule 1. You just have to analyze both resonance structures and ask that question. Which one ever has the most octets is the most significant. Okay, now if we take a look at another example here, okay, you'll see something quite interesting. Now in this example, we're going to have 3 resonance structures. So if that's the case, that has to be positively charged. H2. It's going to be negatively charged right there. And that middle one, that has to be negative as well. Okay, so now we have those 3 resonance structures. Which one is the most significant? We have to start with rule 1. We can't skip steps here. So rule 1, we see that has an octet, octet, octet. Okay? Because what does that nitrogen have? It's going to have a lone pair there. Okay, octet, octet, octet. Octet, octet, no. So based off of rule 1 of these 3 resonance structures, we can say that this is the least significant because it doesn't follow rule 1. Or, well, okay, does not have an octet. So now we have these 2 that are a tie. Rule 1 doesn't break the tie. Which one's more significant between those 2? And that's why we have to go to rule number 2. The structure with fewer formal charges is more significant. Okay? Did you hear that? So the structure with the fewer formal charges is the more significant. So which one's the most significant one? The one on the far left, because it has no formal charges, and this one has 2. So this is the most significant. And then that's the second significant. And then the third one is the least significant. All right? Make sense? Okay, rule 3. CH3. Okay, so we have that one. We can draw a resonance structure that looks like this. Like that. Okay? Now, when we go through rule 1, all the atoms in here have an octet. Okay? And then when we go to rule 2, all those resonance structures have the same amount of formal charges. They all have 1 formal charge. So rule 3, to break the tie in this particular situation, states, other things being equal, rules 1 and 2 being equal, a structure with a negative charge on the more electronegative element will be more significant. And so what we're comparing is a negative charge on an oxygen versus a negative charge on a carbon. When you compare oxygen to carbon, which one's more electronegative? The oxygen atom. So based off of that rule, this would be the most significant in comparing these 2. Now, why is that the case? Why does that work? It's going to come back to a stability argument. Atoms don't want to have formal charges. They want to be neutral. But certain elements can handle a negative charge better than others. So if you could have oxygen in this chair and carbon in this chair, and the doctor's asking them, okay, you have a negative charge, you have a negative charge. Oxygen here will have that painometer. How much pain do you feel? When the doctor asks, and he'll slap down, probably a 4. But carbon, because it's less electronegative, is going to be like, I'm feeling an 8. And so it's a stability argument here. So which resonance form would the molecule rather spend most of its time in? Or look more like? Obviously the one with the oxygen atom, because it's more electronegative. Okay? So that's rule 3 But now I'm going to give you a little twist to see if you can process this concept of stability. All right? So what if we had a molecule that looked like this? Okay, so we have a protonated amide. Versus something like that. Okay? So we're using rule 3 here to kind of help evaluate this one. So which one is more significant? And we have to look at this in terms of stability. What do you think? The one on the right? Most significant. Well, isn't oxygen the more electronegative atom? It is. But we have to think about this in terms of how do the atoms feel. So let's go back to oxygen. Okay? In this chair, it's being interviewed by the doctor. It is the more electronegative atom. But does it have a negative charge on it? No, it's a positive charge. So that oxygen is like, whoa, I want the negative charge, but I'm feeling a positive charge. This is very, very uncomfortable. So it's screaming, 10, 10, 10, 10, 10, this hurts. Because it's an electronegative atom. It wants electrons, but now it has none. So it's feeling a major hurt. Whereas the nitrogen atom, because that's what we're comparing in this case, oxygen versus the nitrogen is less electronegative than oxygen. And so it still sucks, okay? Because it's an electronegative atom. It wants electrons, but it doesn't have them. So oxygen was what, 10? Nitrogen is going to be, say, probably a 6 or a 7. So that would make that the most significant because it's the less stressed out or less in pain. That make sense? Okay, after you take and look at rules 1 through 3, you will eventually encounter a situation that looks like this. Okay. Carbon. Okay, we have carbonate right here. When you evaluate to try to figure out which of these 3 is the most significant and rank them, you'll find that rule 1, tie. Rule 2, tie. Rule 3, tie. So rule 4 is like, who cares, they're all the same. Pretty much. Okay? Once you go through the first 3 rules, that they're all the same, then we'll just say all of these are equivalent to one another. Those contribute to the resonance hybrid the same. Okay? So let's take a look at how do we draw a resonance hybrid. I want to see which problem I did in the last class right here, okay? So let's take a look at this guy, CH3. What was it? That was negative. Okay, we've already seen that one before right there. But now what I want to do is, with that example that we've already went over, we know this one's the most significant, right? Could we draw another resonance structure? What if I just drew that going there? Then we would have something that looks like this. What's the overall charge of this molecule? We We have 2 negatives and 1 positive. So the overall charge is -1. And that matches the other 3. Did I violate any octet rules? Did I form any Texas carbons? No. That's a valid resonance structure. So if we rank these, this would be number 1, number 2, and number 3. This is the least significant and pretty bad in comparison to the other 2. So what we want to do here is take this knowledge of these different resonance forms and draw the resonance hybrid. And so when you draw a resonance hybrid, you're going to take the structure that you see and just ignore double bonds and ignore lone pairs. Just draw single bonds. So we have CH3, C, O, CH2. See how I did that? I ignored lone pairs, just draw all the single bonds. Okay, now, when we take a look at the most significant, what do we see here? With the most significant structure, we see that we have a double bond there, and then it turns into a single bond, right? So to represent that, we just say, hey, we're going to do a dotted line, because that bond right there has partial double bond characters. Sometimes, if we look at it like double bond, single bond, remember it's not going back and forth, it's just a partial double bond. All right? And so that's why we represent it with the dots. Now, do we see another double bond in here that disappears, kind of? Here's a double bond right there. And then it's a single bond. Or if we go this way, it's a single bond. So the carbon-oxygen bond is a partial double bond. See that? How we're making that comparison? Okay. So now, once we figure out which bonds need to be dotted, that's just by looking at all the resonance forms and find the ones that have double or triple bonds. And we add in those dots. Now we have to add in the formal charges. But now it's not a full-blown formal charge, because look, this oxygen right there is negatively charged, but in this structure it's neutral. So how do we represent that in the resonance hybrid? We do a delta symbol like that, and we say, well, that's going to be delta negative. It's partially negative. And then we say, hey, what about this carbon? That's neutral, but it's negative there. So we are going to do a partial negative there. This carbon is neutral, but that carbon there is partially positive. So we do partially positive like that. But here's the kicker here. Of all these resonance forms, which one's the most significant? The one on the far left, right? That's the most significant. And so when I draw these delta symbols right here, I've drawn them the same size. But that doesn't make sense, because the molecule on the far left is the most significant, and the molecule on the far right is the least significant. And so the size at which you draw the delta symbol kind of implies which resonance structure is the most favorable. And so we have to reevaluate how we draw these delta symbols. So because this guy right here is the most significant, I'm going to put a very big delta symbol there on that negative charge. When the negative charge is on the carbon, that's the second most significant. So I'm going to do a smaller delta symbol. And then we see a positive charge on that carbon. That's the least significant of them all. So we're going to do a little tiny one. So the size of the delta is informative so you can understand, what does that molecule really, really look like? Well, it looks like that. And so we put that into some brackets right there, and there's our resonance hybrid. All right? Any questions on that one? Yeah. No. Yeah, you don't. I didn't draw any lone pairs. Yeah.
So it doesn't matter, like, the way we write, for example, like the CH3, we don't have to write it as H. 3C?
You'll see it both ways,
Okay.
but you know
Yeah.
that carbon, you cannot form, that hydrogen can't form two bonds. You know that. But you'll see it in the literature and in your textbook. But if you want to be a little bit more precise, you could have drawn it like that. Okay. Any other questions? Okay, so let's have you guys figure this out. Let's have you guys work together to solve this problem here. Now I'm going to label these. We'll call that A, B, and C. I want you to rank those from the most significant to the least significant. So this kind of resembles the problem from the handout today, question 7. We want to rank those. So as you're working on that, rank those, tell me which one is most to least significant, and then after you've done with that one, I want you to take this structure here, that structure there, and I want you to draw 2 more resonance structures showing the curved arrows. Okay? Because on the exam, if you show curved arrows and then you draw a product that doesn't match the curved arrows, then that's wrong. If you said electrons went from oxygen to a carbon and you don't draw that, then that's wrong. Okay? So that's an oxygen atom right there. Also, answer this. What is the hybridization state of that oxygen? Okay, so draw resonance structures. Answer what is the hybridization state. Okay, so let's work on that. And if we get through it, I have plenty more for us to work with.